What happens when you have product of two functions and you need to integrate them? Well, let's learn that in today's video as we discuss integration by parts. To cover more number of questions and for better clarity, I have further split this topic under two videos. So, let's begin with part 1. Suppose we are given this product where there are two functions u and v in terms of x. Now, in order to integrate it or do the antiderivative, let's recollect as to how did we apply the product rule, which is a part of differentiation. So, d by dx of, if I take any two functions, say fx and gx, the derivative for this was derivative of the first function into the second one as it is plus the first function as it is into the derivative of second. To have a better understanding of product rule, do check out my video on product, quotient and chain rule. You can find the link in the description box and also by clicking on the I button. So let's integrate both sides now. As per the basic rules we discussed for integration, your left hand side becomes fx into gx simply. Your right side, we can split the integral sign for each of the functions individually. So this becomes integral of d by dx into fx into gx dx plus integral of fx into d by dx of gx whole of dx. In order to understand these rules better, please check out the video on Introduction to Integration. Once again, the link is available in the description box as well as by clicking the I button. Let's make a very small substitution here. So I can assume this fx to be some u and this entire term d by dx of gx as, say, v. The moment you do this, just check out what happens. Your left side fx is replaced with u, but gx, in order to get gx from here, you'll have to integrate the two sides. So gx becomes v dx. Next, this is d by dx of u into gx, which is once again achieved by taking the integral v dx. And this one, fx once again is u and d by dx of this is v. You might find this step complicated, but look at it once again. D by dx of fx. So this becomes d by dx of simply u, and your gx once again is attained by taking integral of both sides, which gives you integral v dx. So this is the final answer. If you look at this, we were interested in finding the integral of product of two functions. So let's replace this with the formula. This becomes u into integral v dx minus d by dx of u into integral of v dx, and once you have found this product, take its integration once again. And this becomes the final formula which we need to remember as well as apply to the questions. Please have a look at the entire proof. For our convenience, if I take it as first function into the product of second function, in order to get the derivative, you write the first function as it is into the integral of second function minus derivative of the first function into integral of the second function, and then you integrate the whole product. Now the bigger question is, just like your differentiation, can I take any function to be first or second? Well, the answer is no this time. The reason being, the formula for differentiation was very symmetric. So whether you differentiate the first function first or the second function first, because of the addition sign, it stayed the same. However, here the formula is slightly more complicated. So you need to realize how would you choose your function. You need to focus on the second function. Since it has to be integrated, so we need to choose that function as our second function, which is easily integrable. Because the first function just has to be put as it is or at max differentiated, which can be conveniently done with any function. So do I need to check each time as to which function is better integrable? No. We have a solution for this as well, which is known as the LIATE rule, by which we mean following the order from left to right, you give the preference to the function this way. For instance, I have a combination of some function which is logarithmic and trigonometric, then log gets the first, then log gets the status for the first function and trigonometric function becomes the second one. So on and so forth, you would follow the pattern from left to right. So I have written the formula for reference over here, and this is the pattern that we follow. Coming to the very first question here, according to the pattern, x is a linear, or you may put it under the category of algebraic functions. This becomes the second function because log comes first. So once you have identified this, then it's only the application of this formula. So we end up getting, we get first function as it is into the integral of second minus derivative of the first one into integral of second, and whatever is the output you integrate it again. So this stays log x, integral of x is x square by 2, derivative of log x is 1 upon x, integral of x once again is x square by 2. Cancelling this, we get log x into x square by 2 minus half comes out as it is, and once again integral of x dx would be x square by 2, and we add c right in the end. This is the final answer. Please note, once you become a pro in doing this, you can completely skip this step and move to this one straight away. Have a look at the second question. Now once again you find x square to be an algebraic and sin x to be a trigonometric function. Following the pattern, this time x square becomes the first function and sin x becomes the second. Once we know this, let's get cracking on the formula. So we get first function as it is into integral of second minus the derivative of first into the integral of second, and you integrate it in the end again. So this gives us, if you recollect, integral of sin x was minus cos x. So this gives us minus cos x. Coming over here, we get 2x into minus cos x again. If you look at the situation here, this is not a simple function for which you will directly integrate and give the answer. If you see, this involves the application of your Leibniz rule or this formula once again. So here x is the first function, cos x is the second, and now let's apply by parts one more time. The first one is copied as it is, 2 comes out, and we say it is the first function into the integral of second minus derivative of the first into integral of second, and it is to be integrated in the end. So this side gives us 2x, this time it's only sin x, minus, here we are left with 1 into sin x. After just copying the first two terms, integral of sin x once more is minus cos x, so this gives us plus cos x, and we add c, in the end. Please note you can apply by parts multiple times in the question, but then it should end somewhere. Moving to the third question, now we have a combination of an algebraic and an inverse trigonometric functions. So following the pattern, we label tan inverse x as the first and x as the second function. Now let's move on with the formula. So this becomes tan inverse x into integral of second minus the derivative of tan inverse x into integral of x dx whole integral. X becomes x square by 2 into tan inverse x minus derivative of tan inverse x would be 1 upon 1 plus x square into x square by 2 whole dx. Now the question is, how do you integrate this term? Well, the solution lies within this. If you just add and subtract, take this as the first term and separate out the terms now. So here we get 1 and here we are left with minus 1 upon 1 plus x square. Now moving on, the first term comes out as it is. Integral of 1 is x, and what is the integral for this term? This is tan inverse of x, and we add c in the end. Please note, just like x tan inverse x, you can also integrate these two, but I'll be discussing these questions in the later videos for the reason this requires the use of some special integrals. In the meanwhile, if you wish to, please do try them out. Why do I call this second category of questions as special questions? Well, you would soon realize, look at this one. It does not have a second function attached to it by default, but we can still make use of by parts by introducing the second function on our own. We can multiply this function with 1, which acts as the second function, because log x has the first category and 1, which acts like an algebraic function, takes the second position. And now just apply your by parts. So this becomes log x into integral of second, which would be x, minus derivative of log x, which would be 1 upon x, into integral of 1, which will be x. This time, as you can see, I have skipped writing the formula and have rather applied it directly. So this gives us x log x, integral of 1 would be x again, and this is the answer. Look at the fifth one. Well, it's not mandatory that you have to introduce the second function in the form of 1 only. I can write this as secant x into secant square x. How does that help? Which amongst this has a simpler integration? Even though we know the integral of secant x, which was log mod sec x plus tan x plus c, and integral of secant square x is tan x plus c. As you can clearly see, this is much easier. For the reason you are required to integrate not only once but twice in the question. So, taking cue from here, I take secant x as the first function and secant square x as the second function. Now, you should try this on your own. We get first function as it is into integral of second, which is tan x, minus derivative of secant x, which is sec x into tan x, into integral of secant square x, which is once again tan x. This becomes tan square x. And now one little trick. I can write my tan square x as secant square x minus 1. And now once we open the brackets, this becomes secant cube x minus secant x dx. Now you must be wondering that we began with secant cube x integral and we've landed into a similar situation. Well, that's exactly what we wanted to do, because if I separate these out, I can very conveniently write the integral of secant x over here, and this entire function is simply replaced with I. And thus, we get I is equal to secant x tan x minus I minus integral of secant x dx. This I, once moved on your left, makes it twice of I is equal to sec x tan x. The answer to this integral would be log mod sec x plus tan x plus c. Don't leave your answer here because you wanted to evaluate I and not twice of I. So one last step, this becomes half sec x tan x plus half log mod sec x plus tan x, and c by 2 you may write as simply c dash. That's the required answer. Well, once again, you may like to introduce number 1 as a second function. However, there is another convenient way to deal with this question. Let's put your entire sine inverse x as, let's say, some theta. Now, you know this implies x is sine theta. So, dx would be cos theta d theta. So, your integral gets transformed to theta into cos theta d theta. And now you are ready to apply bypass, which would be much easy. So, this is the first function, this is the second one. We get theta into integral of cos theta, which is sine theta, minus derivative of theta. Now, please remember, this time you are differentiating with respect to theta. So, this becomes 1 into integral of cos theta is again sine theta, and we get theta into sine theta minus integral of sine theta is minus cos theta, so plus cos theta plus c. But don't leave your answer here. Make sure to substitute your theta. So this becomes sine inverse x into x plus your cos theta you may derive from here as under root of 1 minus x square plus c. Wasn't that super simple? Time for the DIY. Please take down the question. Well, it's time to wrap up today's session. I will meet you with part 2 real soon. Till that time, make sure to practice more questions. Share and like this video if you found it useful. Subscribe to my channel if you haven't done that so far. And when you do that, don't forget to click on the notification bell so that you get the message as soon as I upload the video. See you with the next one. Bye-bye.